Hi. So as you can see, I'm sitting in classroom number 308. I'm taking this first ever video for explaining the classification of solids, conductor, semiconductor, insulator, and moreover, today's agenda will be to talk about the Fermi level which is present inside the conductor or semiconductor insulator. So let's start with the classification. We have understood already that the materials are classified as per their electrical conductivity into insulators, semiconductors, and conductors. We have already now are aware about the conductivity of a conductor, which is sigma. Sigma is equal to any mu for conductors, and it is also related to sigma equal to any mu for semiconductors, which are extrinsic semiconductors. Okay, so now today our agenda is to understand about the Fermi level. Okay, first important question is what do we mean by Fermi level? So Fermi level is an imaginary line. Okay, it's an imaginary line which is present inside a conductor or a semiconductor, which is essential to know about the properties of the material when you try to combine the alloys or when you try to create the composites, two or three materials added together, mixed into each other. How exactly that looks like, that's the question. And how exactly they will mix into each other, how exactly the properties will change, that is all what is necessary. And for that, the Fermi level is extremely important. But before to that, before even going for that, we have to understand the types of semiconductors. The first important type is pure semiconductor, and the second type is the impure semiconductor, or which is also called as extrinsic semiconductor. So I'm going to change the page right now, and as you are able to see, all these notes are given to you. These are the properties of conductor. The second part is related to semiconductor. So exactly what all are the varieties of the semiconductor, what are the band gaps, etc. Everything is given over here. So I'm going to talk about intrinsic semiconductors or pure semiconductors first of all. So semiconductors which are in their chemically pure form, they are called as intrinsic semiconductors. That is the definition of intrinsic semiconductor. But what exactly is the variety of charge carriers present inside the pure semiconductor? See, the number of electrons present inside the pure semiconductor is equal to number of holes. That is the property of pure semiconductors. Number of electrons is equal to number of holes. This is what is pure semiconductor. So if number of electrons is equal to number of holes, then how exactly the energy level diagram looks like? The energy level diagram contains two important parts, actually three important parts. The first part is the valence band, the second part is the conduction band, and the third part is the band gap present inside the semiconductor. So the lower one, which is represented in blue color over here, that is the valence band of the pure semiconductor. The upper part where CB is written over here, that represents the conduction band. So these black colored dots which are represented over there, they are nothing but the electrons, and the empty circles which are represented in the blue box, that is nothing but the valence band. So now as you can see, the number of black colored circles is equal to number of empty circles, which represents the pure semiconductor. Okay, so now in this case, the dotted line which is represented in purple color, that is nothing but the Fermi energy, which is exactly represented at the center of the band gap here. Now where is the band gap? Band gap is in between the conduction band and valence band. Everywhere here in this particular region there is a there is a band gap. Exactly at the center of that band gap, Fermi energy is represented, and the symbol for that is E suffix F. That is nothing but the Fermi energy. And the level corresponding to that is called as Fermi level. Okay, so that is for pure semiconductor. Now let's go for what do we mean by extrinsic semiconductor first of all, and then how the Fermi energy of that is represented. So impure semiconductors are N-type semiconductors as well as P-type semiconductor. आता N-type semiconductors मध्ये त्यांना N-type का म्हणतात? कारण की majority charge carriers which are present in N-type semiconductors are electrons. ओके, मग आता हे इलेक्ट्रॉन्स आले कुठून? तर त्याच्यासाठी म्हणून आपण इथे एक डायग्राम ड्रॉ केलेली आहे. सो दॅट डायग्राम इज ऍक्च्युअली अ सिलिकॉन ॲटम विच इज रिप्रेझेंटेड इन ग्रीन कलर, अँड इन दॅट देर आर P-type pentavalent impurities are added. So this is one phosphorus atom which is added per 10 raised to 6 or 10 raised to 7 or per 7 atoms of silicon. Okay, so now there is one extra electron which is present, and that electron takes part in conduction. Okay, so therefore this particular silicon structure, this particular silicon semiconductor is now doped semiconductor with the pentavalent impurities into it. Okay, so this is what is known to you from 12th standard. But now how the energy level diagram for that looks like, that's the real question. And for that we are going towards the diagram which is represented over here. Now the void, this blue colored this thing that represents the valence band, which contains only two holes now. Okay, so the energy corresponding to that valence band is represented as EV, E suffix V. Similarly, now the energy associated with the electrons which are available, that is represented by EC, and the upper part here that represents the conduction band completely. Okay, now the added energies, the added electrons which are there inside this, the added electrons from where they are added because of the pentavalent atom. जो पेंटाव्हॅलंट आपण ऍटम टाकला ना, त्याचे जे 5 इलेक्ट्रॉन्स होती त्यातला एक इलेक्ट्रॉन फ्री राहिला, तर त्या इलेक्ट्रॉनची एनर्जी आपण इथे डोनर एनर्जी स्टेट म्हणून बरोबर कंडक्शन बँडच्या खाली अगदी थोडंसंच खाली दाखवतो, त्याला डोनर एनर्जी स्टेट असं म्हटलं जातं. Okay, so this is the conduction band. That conduction band is full of electrons. आणखीन आपण जे डोप केलेले इलेक्ट्रॉन्स आहेत त्याची एनर्जी इथे डोनर एनर्जी स्टेट मध्ये दाखवली जाते, आणि त्याला आपण आता अशी एनर्जी स्टेट आली म्हणजे आपली आपण म्हणणार आहे की हे आपले एक्सट्रिन्सिक सेमीकंडक्टर्स आहेत. ओके, मग जर का आपल्या एनर्जी लेवल डायग्राम मध्ये फक्त व्हॅलन्स बँड आहे, कंडक्शन बँड आहे आणि फर्मी एनर्जी आहे, मगाशी जी आपण बघितली, परत एकदा त्या डायग्राम कडे जाऊया. फर्मी एनर्जी आहे जी फक्त सेंटरला दाखवलेली आहे, म्हणजे नंबर ऑफ इलेक्ट्रॉन्स इज इक्वल टू नंबर ऑफ होल्स आणि फर्मी एनर्जी ऍट द सेंटर ऑफ द बँड गॅप, अशी जर का एनर्जी लेवल डायग्राम दाखवली असेल तर ती आपली इंट्रिन्सिक किंवा प्युअर सेमीकंडक्टरची एनर्जी लेवल डायग्राम असते. आणि जर का एनर्जी लेवल डायग्राम मध्ये व्हॅलन्स बँड आहे, कंडक्शन बँड आहे, आणखीन एक एनर्जी स्टेट दाखवली आहे जी डोनर एनर्जी स्टेट आहे, कंडक्शन बँडच्या जवळ आहे, तर त्याला आपण एन टाइप सेमीकंडक्टरची ती एनर्जी बँड डायग्राम आहे असं म्हणायचं. Okay, similarly for p-type semiconductor, if there is a silicon structure and inside that we have added one trivalent impurity. आता या केस मध्ये आपण इथे बोरॉन ऍटम ऍड केलेला आहे. मग बोरॉन ऍटमचा एक इलेक्ट्रॉन पेअर बनत नाही, एक होल रिकामं राहतं, तर त्या होलची एनर्जी असते, तर ती होलची एनर्जी कुठे दाखवली पाहिजे सांगा? एनर्जी बँड डायग्राम मध्ये आपल्याकडे एक असतो व्हॅलन्स बँड, एक असतो कंडक्शन बँड, आणखीन एक आपण आता ऍक्सेप्टर एनर्जी स्टेट दाखवतोय. आपल्याकडे आता एक होल ऍड झालं त्यामुळे त्याची ऍक्सेप्टर एनर्जी स्टेट जी आहे ती आपल्या व्हॅलन्स बँडच्या जवळ ऍड झाली, त्यामुळे इथे आपण दाखवतोय ई ऍक्सेप्टर एनर्जी स्टेट विच इज ऍडेड नियर अबाउट टू द व्हॅलन्स बँड. ओके, तर आता हे आपली झाली एनर्जी लेवल डायग्राम. म्हणजे एनर्जी लेवल डायग्राम मध्ये काय काय ठरलं आपलं? जर का प्युअर सेमीकंडक्टर असेल तर फक्त व्हॅलन्स बँड, कंडक्शन बँड आणि फक्त फर्मी एनर्जी स्टेट ऍट द सेंटर. ओके, पण एक्सट्रिन्सिक सेमीकंडक्टर जर का असेल तर त्या केसमध्ये काय होणार आहे? व्हॅलन्स बँड, कंडक्शन बँड आहेतच, त्याच्याशिवाय जर का आपण इलेक्ट्रॉन्स ऍड केले असतील तर ते कंडक्शन बँडच्या जवळ डोनर एनर्जी स्टेट क्रिएट करतील, आणि जर का आपण होल्स ऍड केले असतील तर ते व्हॅलन्स बँडच्या जवळ ऍक्सेप्टर एनर्जी स्टेट क्रिएट करतील. ओके, मग आता हे सगळं आम्हाला समजलं. मग याचा उपयोग काय करून घ्यायचा आहे, तर याचं आपल्याला रिअल लाईफ ऍप्लिकेशन काय आहे? तर ज्या वेळेला दोन मटेरियल्स एकमेकांमध्ये कंपोजिट बनतात ना, when they create some kind of alloy, when they create some kind of composite, or suppose if you try to talk about the PN junction diode, then the electrons migrate from N region to P region, holes migrate from P to N. Okay, but till what time, what exactly is the controlling factor which controls the transition of electrons or holes from one region to the other region? That's the real question. So basically Fermi level acts as a reference point that controls the transition of the electrons and holes from one region to the other region, and therefore we have to understand what exactly is the position of Fermi energy, what do we mean by Fermi level, and where exactly that Fermi level lies inside the extrinsic semiconductor. These are the questions which we want to find out the answers for. Okay, so let's go ahead. Now in this particular notes, there are examples which are given related to band gap energy, and there are some questions which are related to conductivity also. So the conductivity part we have already taken inside the lectures, and now therefore I'm not going to take it in the online right now. Okay, so if as and when time permits, I'm going to continuously create these kind of videos with the help of Karthik. Karthik Gaikwad has helped me to create these videos, excellent videos, and therefore we are going to take his help continuously to create the videos and go forward with the things. Now, the Fermi level in case of semiconductors and conductors is defined in altogether different manner. Okay, in case of conductors, the Fermi level is defined as the highest occupied state in the highest band. Okay, so let's go to that diagram first. I don't know how come this numericals are here. Here, it's a distribution function. Okay, so Fermi level in conductors is defined as the highest occupied state in the highest band, and in case of Fermi level, it is nothing but the average energy, average of the energy of electrons in conduction band and holes in the valence band when they are weighed as per their energies. So I'm going to show you that particular diagram here. So this diagram represents the energy level diagram for semiconductors. So this first diagram represents the valence band, conduction band, but the energy gap has got exactly at the center Fermi energy. So the first important diagram is for the intrinsic semiconductor. Okay, all of you have understood this. So Fermi energy basically represents the average of the energies of the electrons in conduction band and holes in the valence band when they are weighed as per their energies. Fine. Now, in case of N-type semiconductor, what happens is the number of electrons is more. So the weight on the conduction band side is more as compared to the weight on the valence band. And therefore, Fermi energy, since it represents the average energy, the average shifts towards the conduction band. Okay, so Fermi energy in N-type semiconductors is represented near about to the conduction band, and the Fermi energy in case of P-type semiconductors is represented near about to the valence band. Right? So this is how the Fermi energy, position of Fermi energy level shifts because of the presence of the majority charge carriers. If the majority charge carriers are electrons, obviously the weight on the conduction band side will go on increasing, and therefore the Fermi energy will shift towards the conduction band. And if the number of majority charge carriers are holes, then the weight on the valence band side will go on increasing, and therefore the majority charge carriers are since the majority charge carriers are holes, the Fermi energy will shift towards the valence band. Okay, so this is how the energy level diagram will look like in case of pure semiconductor and extrinsic semiconductors. Now, the Fermi-Dirac distribution function represents the probability of finding the particle with the energy state E. Okay, since we are trying to talk about the Fermi-Dirac distribution function, we are going to talk about the probability distribution function. This PE, what is this P? P represents the probability of finding an electron. This is what the definition of P is, or probability of finding the charge carrier with the energy state E. This is the difference. This is our definition of PE. Okay. So when you're talking about the probabilities, the maximum probability of finding anything under the sun is 1. Maximum probability of finding the particle is 1. Okay. And therefore all the function lies in the denominator. In the denominator it is 1 plus e raised to e minus ef, where E is the energy at which you try to find out the probability. EF is the Fermi energy of that particular material divided by K, where K is the Boltzmann constant and T is the temperature at which you try to measure the probability. Okay, so PE depends on the Fermi energy and it depends also on the temperature at which you try to measure the probability of finding the particle. Okay, so Fermi energy is extremely important when you try to find out the probability of finding the particle. Okay, now why exactly do you need the probability of finding the particle? The probability at any given energy state E is very important because that energy E defines whether that will be able to form an alloy with the other materials or it will try to form some kind of composites. Okay, so let's try and understand what exactly is the probability of finding the particle above the Fermi energy EF. Okay, now these probabilities we are trying to find out for conductors. Okay, in case of conductors, how the Fermi energy is defined, let's go back and try and understand again. In case of conductors, the Fermi energy is defined as the highest occupied state in the highest band at 0K. Okay, it is the highest occupied state in the highest band at 0K. So, what is the probability of finding the particle with the energy state E, which is beyond EF? Okay, probability of finding the particle beyond EF will be obviously 0 because EF is the highest occupied state in the highest band. Okay, so no energy state beyond that is filled at all. Okay, all the energy states up to EF are filled. Beyond EF, no energy state is filled. So at T equal to 0, K, probability of finding the particle with the energy E which is greater than EF should be 0. Okay, so let's try and understand whether this Fermi function helps us to get that. Okay, so PE is equal to 1 upon 1 plus E raised to E minus EF upon KT. Now for E greater than EF, the exponent E minus EF upon KT will go to plus infinity, right? Because E minus EF will become plus some positive number because E is greater than EF, and T is anyway 0 because we are talking about the 0 K temperature, and therefore PE is equal to 1 upon 1 plus E raised to infinity, which is 1 upon infinity, and therefore that probability of finding the particle goes to 0, right? So this is the first important part. Now the second important part is that the probability of finding the particle. What is the probability of finding the particle when the energy of the particle is less than the Fermi energy, right? Now you know again that the EF is the energy state which is the highest occupied state in the highest band. So all the energy states below EF are completely filled by the electrons, and therefore probability of finding the particle below EF will be maximum, which is 1. Okay, and therefore let's try and understand whether this Fermi function helps us to get that. So P is equal to 1 upon 1 plus E raised to E minus EF upon KT. हे Fermi functions आणि पाठ करून टाकायचं. Okay, मग आता E minus EF upon KT will become now negatively infinite because E minus EF will generate a negative number divided by 0 will generate minus infinity. So suppose if I substitute that value, then the Fermi function comes out to be 1 upon 1 plus E raised to minus infinity, which is nothing but 1 upon 1 plus 0, which is 1 again, right? And therefore probability of finding the particle becomes 1, or which is maximum. Okay, now let's try and find out what exactly is the probability of finding the particle at the Fermi energy itself. Okay, so for example, there is a first bench, and what is the probability that our Shreyas will occupy that first bench or he will not occupy that first bench? I think I have taken this example in our N division also, where Sneha was sitting on the first bench, maybe I remember, or Yadav was there on the first bench. Or what is the probability that the first bench will be occupied by Yadav, or it will not be occupied by Yadav? So the probability comes out to be 1/2. Right, because there are two possible events, out of that one will be the favorable event. So exactly similarly, what is the probability of finding the particle at the Fermi energy itself? It will be equal to 1/2. Either the particle will occupy the Fermi energy or it will not be, right? So let's try and use the Fermi function and try to figure out whether the probability is 1/2. So P is equal to 1 upon 1 plus E raised to E minus EF upon KT. Right? So since E is equal to EF, that comes out to be E raised to 0, and therefore probability is equal to 1 upon 1 plus E raised to 0, which is nothing but 1 by 2. So probability of finding the particle at E equal to EF comes out to be 1/2. Right? So now we have to draw the probability of occupancy curve, and that curve is represented somewhere over here. So obviously there are two axes. One of the axis is energy axis and the second axis is probability of finding the particle with the energy E. Okay, so the highest number on the probability axis is 1, right? So on y-axis, the maximum number is 1, the minimum number is 0, and in between 0 and 1, we have got one more probability, which is 1/2, and therefore we have to draw three important points on the y-axis, which is 0, 1, 1/2, right? That these are the three important points. Now on the energy axis, we have got to represent only one important point, and that is nothing but the Fermi energy. Okay, what is the probability below Fermi energy? That we are interested in finding out. How much is the probability beyond EF? We are interested in finding out that also. And what is the probability of finding the particle at EF? We are also trying to find out what exactly is the position of what is the value of probability at the Fermi energy. Okay, so therefore only one important point on the energy axis, which is EF. ओके, मग वाय ऍक्सिस वरती तीन महत्वाचे बिंदू काढायचे, 0, 1/2 आणि 1, आणि एनर्जी ऍक्सिस वरती एकच महत्वाचा बिंदू काढायचा, त्याला म्हणायचं फर्मी एनर्जी. ओके, मग आता बिलो EF, what is the probability of finding the particle below the Fermi energy? It is nothing but the maximum, and therefore probability of finding the particle below EF is 1, and therefore you have to draw one straight line below EF. At all values of E less than EF, probability of finding the particle is 1. and therefore I have drawn 1 over there. Similarly, probability of finding the particle beyond EF is going to be 0 because all the energy states below EF are filled, but no energy state beyond EF is filled. All the energy state beyond EF are empty, and therefore probability of finding the particle beyond EF goes to 0. Okay, and therefore it is represented by a straight line beyond EF. So this is our case 1, this is our case 2. Now at E equal to EF, the probability of finding the particle is just 1/2, and therefore it is represented by this particular point here. Okay, so this is the point which represents the probability E equal to EF. Now, when you increase the temperature, then at some temperature which is greater than 0 K, some of the energy states below EF are empty and some of the energy state beyond EF are filled. Okay, and therefore the probability of finding the particle below EF goes on decreasing and probability of finding the particle beyond EF goes on increasing, and this is what is represented in the form of shape S here. When with the increase in temperature where T1 is greater than 0 K and T2 is greater than T1. So when the temperature goes on increasing, some of the energy states below EF are vacated and some of the energy states beyond EF, they are completely occupied by the charge carriers. So this is what is represented over here in this particular Fermi function or the probability of occupancy curve, right? So I think I'll stop here at this point right now. So let's try and understand how exactly that recording looks like. And after seeing this particular recording, by getting the feedback for this particular recording, I will try and understand how exactly to proceed further. Okay, thank you very much.